So let's talk about electrophysiology, right? Electrophysiology is the idea that recording electrical signals from a organ system or cell can provide useful physiological recording. Now, for some things, this may be, I don't want to say a stretch, but possibly not the most natural approach. But for the brain, it's pretty good. So we have known since Galvani in the 1780s that there was some link between electricity, nerves, and muscles. And that linkage was pretty poorly understood for quite a long time. Now, the first extracellular action potential was recorded in 1868 by Bernstein, which you see there. It was called the negative Schwankung, which is a pretty good name. And still, they didn't fully understand what they were seeing. They knew it had something to do with nerves. Of course, just we'll get more explicit about this later, but when I say extracellular, I mean that the signal that was being recorded was recorded from outside of a cell. So extracellular outside of a cell versus intracellular inside of a cell. But within sort of 50 years, things were getting a much clearer, right? And so this led to this idea of the rate code, proposed by Lord Edgar Adrian and Zoderman in the 1910s and 20s. And this is what their recordings look like. Pretty rough to modernize, right? You can see the hand-drawn A, B, and C here. But what they are doing is they are hanging weights off a muscle and looking at the Golgi tendon organ output, and the white bit here is showing the rate of action potentials as they hang various weights. Now you can see what they're what they're trying to show here, but the point is that as they hung more weight off the muscle, they got a higher frequency of action potentials. And here it is in a graph. All of a sudden, it's clear to see what they're talking about. And this was the beginning of the rate code. The idea that when neurons want to send a more, right, whatever signal they're coding for, if they want to send more of that signal, they fire with a higher frequency. Of course, this is related to the concept of the all or none action potential, right? Because previous to this, somebody could have said, well, if a neuron wants to send more, it just fires a bigger action potential. And Edgar Adrian was the one who said, no, all action potentials are the same size. What a neuron does is it fires more. Oh, and, I want to be clear that that was a pretty important finding. Okay, so then we go forward. We're talking about my friends Hodgkin and Huxley again, and we get the first intracellular recording of the action potential in 1939. And of course, they showed that the action potential wasn't caused by the membrane breakdown theory. Now, the use of intracellular methods developed a lot in the next 30 years. So Hodgkin and Huxley had a giant squid axon. It's about a millimeter across. They could physically thread a wire down the middle, literally tie knots on the end of the axon so that they had an intracellular recording. Obviously, that kind of approach doesn't work for a mammalian neuron that might only be 20 microns across. So here they're doing something called current clamp. In all of these intracellular methods, the thing you're talking about is not what you're measuring. So in current clamp, you don't measure current, you measure voltage. And that's what we see here, the transmembrane voltage, depolarizing and hyperpolarizing during the action potential. In voltage clamp, you don't measure voltage, you measure current, right? Because what it's talking about is what do you keep constant. So in voltage clamp, you keep the voltage constant and measure the current, while in current clamp, you keep the current constant and measure the voltage. So Hodgkin and Huxley not only measured this action potential, they didn't quite invent voltage clamp, but they popularized voltage clamp. And with that, they were able to generate the complete understanding of the action potential, and then they won the Nobel Prize in 1963. So as I alluded to, Hodgkin and Huxley did their intracellular recording with a wire, which you can't use for a mammalian neuron or an insect neuron, really. It's only the weird giant axon of the squid that you can use it for. So in the 70s and 80s, an idea called sharp intracellular recording or sharp microelectrode recording. And you can see what a sharp microelectrode looks like. Here it is there. Here's the scale. That's 300 nanometers. That's less than the wavelength of light. So what we have is a glass tube, a hollow glass tube filled with saline, and it gets heated up, and then you pull it apart, and the melty bits form a thin thread, but it's still hollow all the way down the middle. So you can then literally jab that into a neuron or any other cell for that matter, and get intracellular access. And then the membrane magically sort of seals around the glass, and you have intracellular access. So I just want to shout out Australia. It's always been at the forefront of electrophysiology. So this was perfected by Alan Finkel, who was um, Australia's chief scientist, and he's either just about to go up or already has gone up in the Virgin Galactic because he sold his company that allowed the easy or relatively easy sharp electrode recording to an American company for many millions of dollars. So, sharp electrode, you get inside the cell. Now, the problem is sharp electrode recording is a pain. It's super fiddly. It goes wrong. You got no idea why. So in the late 70s, Bert Sackman and Erwin Neer invented patch clamp recording, which allowed fast, stable intracellular recordings. It allowed the recordings of single ion channels. That's what we see here. So this is the current that is going through a patch of membrane, and each little square step is a single ion channel opening and allowing current to move. And they're applying acetylcholine and another cholinergic agonist that's just escaping me right now to this patch of membrane and opening nicotinic acetylcholine receptors, and so sodium is moving through the channels and they can record that. And they won the Nobel Prize in 1991 for inventing this. Then Greg Stewart, an Australian, went to work with Sackman, and together with somebody called Hans Dott, they made a big discovery, which was you can see neurons in a brain slice, and if you can see it, you can patch it. So this allowed the visualized patching of cells. So this is a layer 5 pyramidal cell. Here is an electrode recording from its dendrite. This is a different recording of another layer 5 pyramidal cell. They've filled the electrode with a fluorescent dye, and that fluorescent dye can then move down the pipette and fill the cell. Now, filling the cells largely just because it looks cool, but it's the electrical access, right, that they're able to record directly from the dendrite or later directly from the axon. Because if you can see it, you can patch it, even large presynaptic terminals. And this gave us a whole new idea about the fact that dendrites are probably much more than just passive funnels for current to create action potentials.